Hi, I'm Matt Oliva. This is my Lab 5 for Physics 2212, magnetic braking with Faraday. So the major concepts in this lab are Faraday's law, magnetic field, the Biot-Savart law, Newton's laws, flux, and motional EMF. Faraday's law is that induced voltage in a circuit is proportional to the rate of change over time of the magnetic flux through a circuit. The Biot-Savart law states that it finds a magnetic force on a current-carrying ring. Newton's second law is also used in this lab. That force is equal to the mass times acceleration. And Newton's third law is also used, which states that every force has an equal but opposite reaction force. So for the physical experiment, materials involved foil, a bar magnet, a phone, and a tube. The procedure was to suspend the bar magnet just above the suspended tube with tinfoil and set up a smartphone and record the magnet being dropped through the tube and measure the time. So physical measurements, the tube was 0.3 meters, the foil was 0.017 meters, inner radius 0.015 meters. The mass of the magnet was 0.025 kilograms, and the magnetic moment was 0.72. Our average experimental time to fall through the tube was 0.53 seconds. So for the code, first we entered our data from our physical measurements to match our experiments. This part uses the function from Lab 3 to calculate the magnetic field from the bar magnet. This code uses the Biot-Savart law to complete this. Now we create a function to find the rate of change of flux through each ring due to the moving bar magnet. This uses concepts from Faraday's law. Now we use Newton's second law to determine the gravitational force on the magnet, which is mass times gravity. These lines of code find the magnitude of the force of the B field at each ring. And here we calculate the net force on the magnet, which is the sum of the forces, and update the magnet's velocity and position. Now the model that this code creates displays the velocity of the magnet versus time. Through the majority of the fall, as you can see, the velocity remained unchanged, meaning that the net force on the magnet was at or very close to zero. The magnetic force canceled out the gravitational force in some places. So, as a comparison, the model predicted 0.57 seconds. Experimentally, we measured 0.53 seconds. Relatively accurate model data could have been made more accurate if it accounted for air resistance too. Question 1 asked, what if the resistivity on the conductor were reduced as close as possible to zero? How would the dynamics change? This would lower the resistance from the foil, increasing the current. This creates a stronger force on the magnet, which would cause it to fall even slower through the tube. Question 2 asked, what if holes or slots were cut into the tube? How would this affect the ring currents in our model? So, if holes and slits were cut into the tube, it would reduce the amount of conductive material in which a current is generated. So this, in turn, would reduce the magnetic force on the magnet, which would cause it to fall more quickly through the tube. Thank you.